Okay, this video I'm going to show you on how from the previous example 10.4 you can use the equation or the composition that you have derived just now. Okay, then calculate the oxygen required for the aerobic digestion, right? So you know that aerobic digestion need oxygen to digest the waste. Okay, so you can use this equation, okay, to know the amount of oxygen produced. Okay, the oxygen required for the aerobic process. Okay, so this one is the equation on oxygen requires to oxidize the ammonia, right? So let's have a look on example 12.1. Okay, so estimating air requirements, determine the amount of air required to oxidize 1 ton of waste, having the chemical equation of this. Okay, so instead of our example just now, we produce this, so we may continue using this equation. Just imagine you are using this equation instead of using this one, but for this video I will elaborate on using this formula. All right, okay, so you can see the continuation, right? So when you have calculated the composition from the previous example, you can use it in this example, right? So here we're using this equation 12.1 in order to calculate the amount of oxygen required per ton of waste being used, right? So A is actually for carbon, B is for hydrogen, C oxygen, and D for nitrogen. So you just follow this equation, right? So take the A, okay, from the equation A is 50. Okay, so you substitute all the amount here, right? And then this is the required coefficient. So this is your total up the coefficient A, B, C, D, right? So the next part is using this coefficient in this equation. So you can, this 1354 is actually the total molecular weight of this equation, of this formula, right? So this similar goes for 1736, okay, and then CO2, H2O, and ammonia. So the amount of oxygen required per ton of waste, so you know this is the formula for your waste. You have 1 ton of waste is equals to 1000 kilogram. So from this equation you may see that 1736 comes for the oxygen. Okay, that's why it's 1736 over 1354 based on the molecular weight calculate from the composition of your waste. Okay, times 1000 kilogram is 1 ton of your waste. So you get 1.282 10 to the power of 3 kilogram per ton of waste. Then next is you want to calculate how much oxygen is needed to oxidize the ammonia. So from this equation you see this is the total of molecular weight for ammonia, oxygen, water, and also nitric acid, right? So the oxygen, okay, sorry. So oxygen from this equation is actually, okay, this one, ammonia is produced from, so you see ammonia produced from this waste, so that's why it's 17, right? 17, okay, over total amount composition of the waste is 1354. But somehow from this equation only, okay, only this much of oxygen needed to oxidize ammonia. So 64 over 17 times the mass of the waste, which is 1 ton or 1000 kilogram. So you get this one. So total up the amount of oxygen that you use to oxidize the waste, including to oxidize the ammonia, is actually this value plus this value, right? That's why for the next page we have this value. Okay, so you total up, you will get 1329. And then this is the amount of oxygen. So the mass of air required. Okay, we assume this is like a rule of thumb, 23% oxygen in the air. Okay, so it's like oxygen is equals to 23% from the air. So you have your oxygen calculated, you need the amount of air. So that's why 1329 is from the oxygen just now. So you will get the amount of air is about 4742. So volume you may get from density is equals to mass over volume. Okay, so you will get that volume. So density of air, you can refer to the appendix at that temperature. So given here is 1.2928. Okay, that is for aerobic digestion. What about anaerobic digestion? Okay, same thing. Okay, it can be continuation from the previous example, right? But okay, instead you're using the different kind of equation. So here you may see it's methane. Just now we have amount of oxygen. So this is methane because anaerobic we didn't need oxygen. So follow back the ABC. So you listed it out here, right? And then use this coefficient. Okay, similar goes like earlier in example 12.1. Okay, so you have calculated the amount of composition of the waste and then water and then methane. So these two equation, the difference is in these two equation compared to the aerobic digestion just now. Okay, so you wanted to calculate the amount of methane produced per ton of waste. So here you may refer this is methane. So the amount produced is 434 over 1354, the amount of waste, times per ton 1 ton of waste. So you will have methane, this much of methane will be produced per ton of waste. Okay, so how much of volume of methane gas? So you use the density. So density, it might be given in the question or you may refer to the appendix as well. Right, so I think that's all to show you a few examples that can relate to each other. All right, good luck.